Hello and welcome back. We now start our journey into neural networks and deep learning and start with a general introduction to the topic. Let's draw the connection to the biological brain. It's a very simplified picture really, but we can start from imagining that we have like 90 billion brain cells and each neuron is connected to thousands of other neurons. And in this very simple picture, our memory is built from connections between patterns. So for example, we don't store memories as DNA strands. Memories are stored in the way neurons are connected to each other. It's really a very simplified picture, but it helps to understand where the idea of neural network come from. So how do these neurons work? It's even more simplified really. So we have our neuron and the dendrites are the connections to other neurons. This is like the input. Then we have a sort of axon, this long object to the right that also ends in dendrites, and this is like the output and the connection of this neuron to all the other ones. And in this very simple picture, the neuron gets an input from the other neurons, processes this with and delivers an output via the axon to other neurons. And whether or not such a neuron produces an output is determined by an activation function. Once we exceed a certain threshold, this neuron gives a signal to others. So let's abstract this even more and say we have n inputs and then we sum them together. We determine the output, this is the activation function, and then we have a different number of outputs, this is our connection to other neurons. So there are a number of activation functions. In biology there's one specific one, but now that we move to artificial neural networks we have a choice and we need to determine how they are. The key thing about these activation functions is that they're non-linear, and this enables neural networks to learn complex tasks. Previously, for all people like me, it's the traditional sigmoids and tangents that we grew up with. The more modern ones are ReLU and similar ones. And this is how we build networks. We have the same fundamental principles. We have an input neuron that produces an output based on the activation function. So this is the same key idea from the biological brain, and really this is where the similarity ends. The key questions we need to ask ourselves are now, how do we arrange these artificial neurons? That means how many do we have and how do we connect them to each other? And then obviously we need to have a means to train this neural network, and there we have to address the questions that we will focus on what we do with the activation function and how do we have this weights in the abstract concept of the neuron where we combine the input from the others. So if you color code it like this, we have in yellow the input node, in green intermediate or hidden nodes, in blue the output node. The simplest thing we can do is have a simple feed-forward neural network. So we have a few input nodes on the left, and these are connected to hidden or intermediate nodes, and we have an output node. So this is where the simple or shallow networks started from many decades ago. With the advent of deep learning, what we really do is make these connections more complex. So a modern deep learning network is larger and also has many more layers. And the way these different neurons are connected then defines how a neural network is working. Let's start with the simplest part, the feed-forward network. So we have the input nodes. These are our features, for example. We don't go to advanced methods like image processing quite yet. So here we focus on tabular data. These are our feature variables with numerical values. Let's only just have one hidden value, only one hidden intermediate layer with m nodes, and we only have one output node. Or we can have n of those. And the feed forward means that information flows from input to output. And this kind of network is like the traditional setup maybe before 2012 or so. So how do we train such a simple neural network? Our topology of the network is now defined by the number of neurons in the input, hidden and output layer, and also how these are connected. In feed-forward networks, which we just discussed, we assume that each node is connected to all others. We also need to initialize all those weights, and remember those weights are really the strength of the connection. So we have the neurons and these connections, these are the sort of network weights, and we need to set an initial value for those. Because we need to train this method, we need to distinguish between good or bad predictions. In the end, we want to have, for example, a prediction for a specific set of variables. So the simple neural network, we put the variables in on the input layer, and then this network is used to make a prediction in the output layer. There are two main cost functions that we use, the so-called cross entropy that is used for classification, and the residual sum of squares for regression. Now that we have a cost function, we also need to have a method to adapt these weights to reduce this cost function. And there are two main approaches that are popular at the moment. This is called backpropagation and attention. So the key ingredients, to recap, is that we have a topology that is defined by the number of nodes in each of the layers and the connection between these nodes, and these are the network weights. Once we have initialized them, we need to settle on a cost function to discriminate between good or bad predictions. And now we need to understand how we change those weights or the strength of the connection between the nodes. One of the very commonly used approaches is called backpropagation. And the main idea is the following. We take the current setup, calculate a prediction with the current weights. Then we compare those predictions with the true labels in our supervised learning approach. This is where we use the loss function. And now we need to somehow calculate a change of weights to reduce this loss function. And once we've calculated this change in weights, we need to update and propagate this change throughout our network. And this is an iterative process, so we repeat the whole idea over and over again. And this is illustrated also on the right in the so-called forward pass. We use the network as is to get the prediction y hat, and in the backward pass we need to calculate and update the weight changes. Most commonly this is done with gradient descent. Here we determine the slope of our cost function with respect to the weights. So really what we want to do is we have our cost function that determines how well our prediction is relative to the true value we want to predict. And the gradient is then calculated such that we calculate how and in which direction we need to change these weights to make the cost function smaller. So this determines our change in weight, and we also need to give it a parameter that determines how quickly we go in this direction. In a nutshell, what we want to do here is to find the valley where the prediction matches the true label best. So let's do this step by step. For any neuron in the output layer, OJ, right, we can calculate the following. We have the transfer function, S, and the combined weights with the input from the previous layer. Now we have the cost function, but there is no explicit dependency on those weights. So that means mathematically we need to employ the chain rule repeatedly. So we start in the output layer because here we know the values of the true label y and the prediction y hat. And then we work our way backwards to the input layer by applying the same formalism until we reach the input layer. So graphically on the right hand, what we see here on the top is we have the input features, we get the sum of weighted inputs, apply the transfer function and get the output for this neuron. And to get the change of weights, as we said before, we want to go in the direction where the error is smallest and where the prediction matches our true labels best. So we take the partial derivative with respect to the weights. And because there is no direct dependence, now we need to use the chain rule. If we use then the formalism for the network, the formula for OJ equals S and of Xi, right? And we can see there's a dependency of the cost function on the output node, because we are in the outermost layer where we know the true value and the prediction. And we need to work then our way towards by applying the chain rule towards the weight. And this is what's shown on the bottom right. So in the output layer, we have the following formula. We know y and y hat. In the output layer, the output is y hat. So the output of the last neuron is the prediction. So this is what we do here. For example, for the residual sum of squares, we can calculate this explicitly. Then we move to the next part. Here we can see that this is the derivative of the transfer function. So here we need to have a formula for this. And step by step, now that we move on to the last one, this is really the input to this node. So the output is the sum of the weighted input after the transfer function, so we need to have the derivative with this. And then we have the sum, the weighted sum of the inputs. So the input to the output layer is the output of the last intermediate or hidden layer, right? And this is how we propagate the weights from the output layer backwards towards the input layer, and this is why it's called backpropagation. There are some obvious problems with this that we need to address when we train neural networks, and one of them is the vanishing gradient problem. In the traditional networks of maybe 20 years ago, the traditional transfer function was the tangent hyperbolicus, and we can calculate the derivative analytically. However, it is non-zero in only very small regions, and it worked well at the time. However, this is a problem in deep learning because we have now so many deep layers in our deep neural network. So very often we propagate numbers that are very close to zero. And this led to the development of all the other ones, the other more modern activation functions. We've also seen in our definition of how to change the weight that we have this free parameter, the learning rate. This determines the step size in our gradient descents. The change of weight is proportional to our gradients, but we also need to determine how fast we want to go in this direction. So if this learning rate is far too small, learning is usually very slow. If this learning rate is very large, training becomes unstable, so we cannot evaluate the properties of the gradient properly. A good best practice is to use an adaptive learning rate scheme. We want to have a large learning rate at the beginning when learning is fast, and we want to have a small one towards the end. Or we can also use a cyclic one, and a number of people have made good experiences with this. So let's put this into a more practical example and start building our network, and we use the TensorFlow Playground for this as a web application, which is quite nice. So let's use a very simple one. We have only 2 neurons, and we create the data like the 2 blobs shown on the left. We use a linear activation function, and remember, we earlier said that neural networks really need a nonlinear one. But what happens if we start with a linear one? We have these simple 2 blobs, and this can be solved with a straight line. Obviously, we don't need a complex neural network for this simple task, and the simple neural network with 2 neurons in the input layer for the features and 1 in the hidden layer learns this perfectly. Now let's take a slightly more complex case and go to this nonlinear case. We have 2 blobs, but they're separated differently. We have essentially this square arrangement from our 2 classes. So obviously this cannot be separated with a linear model or a straight line. So our first assumption would be, if we train this network for a very long time, then we will be able to learn this. And the simple network can train for a long time, but it doesn't learn it. So linear neural networks cannot learn nonlinear relationships. This is really not surprising, but it's good to make this explicit. So what could we do? We could add more features. In particular, we could add, for example, more hidden layers, and this sort of gives it more flexibility. It still doesn't learn it. And now we come to different approaches. We still have an activation layer that is linear, but now we give it specific features. In particular, we use our expert domain knowledge, in this case, we know how we generate the data, and create this pairwise interaction. And then even with a linear activation function, the neural network can learn this, and this is part of this feature engineering. We build features from our domain knowledge, and we as humans know what good features would be. And the neural network is, in this case, simply a linear regression model that combines those features optimally. But what we can also do is build better networks. We change the activation function to something non-linear. So here we have a small neural network, but we give it only the very basic features that have not been able to recover this more complex data with a linear function. And this is the approach towards modern deep learning approaches. We make the networks more powerful by adding more layers and optimize their topology, but also use different activation functions. So in this sense, neural networks learn end-to-end from the data. We give it the raw data, and we don't create features ourselves, but we let the network learn them in the intermediate layers. One of the key things we need to avoid is overtraining. As training progresses, the cost function gets smaller and smaller. And on the training sample, we observe this effect. So this sounds like a good thing, right? Apart from the fact that maybe on an independent test data sample, at the same time, the error starts to go up again, and this is what's called overtraining. The network starts to learn noise and not the fundamental relationships in the data, but it's picking up random fluctuations, and this is not what we want to do. So how can we do this? One popular approach is to do early stopping. So we measure the error on the test and training sample and then stop once the error on the test sample starts to go up again. We can also add some regularization constant to it, similar what we did in regression, for example based on the L1 or L2 norm, similar to loss and ridge regression, and this is called weight decay. We can also involve a pruning scheme. That means during training we remove nodes and connections that have small weights. This means that we sort of lobotomize our neural network and make it smaller. One of these approaches is called a dropout, and it's called like this because they randomly drop nodes and connections. During training we drop different connections and nodes at each iteration, and this effectively means that we train many small neural networks and they have less capability for overtraining. During inference then we need to apply corrections to avoid that nodes contribute several times. Maybe let's finish with a quote about modern deep learning. It's called the bitter lesson from one of the giants of artificial intelligence. Researchers seek to leverage their human knowledge of the domain, but the only thing that matters in the long run is the leveraging of computation. There are psychological commitments to investment in one approach or another, and the human knowledge approach tends to complicate methods in ways that make them less suited to taking advantage of general methods of leveraging computation. So what this means, and results have shown this in the recent years in particular, that although humans are very good at understanding the domain and building features, in many cases modern deep learning approaches where the features are built by the neural network themselves have won in many areas.